Hi Mason, hi Steven, how are you?
Good. How are you?
Oh, doing good, thank you. Hi Jofan.
No.
Oh,
Hello,
hi Amir, how are you?
how are you? Good morning.
Good morning, doing good.
Winter start again today. Weather is snowy.
One winter is not enough.
We should call Fargo the frozen land forever.
It's frozen too.
I believe Fargo is in the running for best university campuses in the United States, alongside Alaska.
Yeah, last week the weather was great, but from today, I think for 2 or 3 days,
There will be snow.
yeah, would be snowy and go below the zero temperature.
It's dangerous when it gets hot too quick, then we are getting floods. So when it ramps very slowly, it's safer.
Because of melting snow, you mean?
Huh?
Because of melting snow? Why?
Yeah. Why? Let me show something.
No, yeah, I understand. It may make some floods or.
Well, I'm personally interested in slow melting of snow.
Oh, you live right on the river.
Yes, because the
Oh my
water
god.
approaches right to the windows.
Yeah, this is really bad. Yeah, it's very dangerous for you. We pray that.
Thank you. Who else? Oh, hi Rebecca.
You mute the voice, Dr.
I did. No. You think I have muted voice?
Actually, come here.
Huh? You don't hear me?
We cannot hear you, no.
Interesting. Then I disconnected and connect back.
No, friend, can you hear me?
Yes.
Okay, I'm disconnecting.
Everyone, we have a guest in
Oh.
the lecture today.
Oh,
You also have a cat. Beautiful.
super.
2 cats, actually. The other one is Bone White. Oh,
Female or male?
she's very noisy when she doesn't get what she wants. And right now, what she wants is to try and knock my coffee off of the top of my cup.
Can you hear me now?
Yes.
Yes.
Excellent. Okay, I think we have sufficient attendees. So I suggest we start, and whoever is not on the connection will probably watch the recordings. So I'm placing the connection onto sharing the screen. Okay, so we are in the computational chemistry class, and the goal is to characterize properties of materials through computational modeling. We are getting the theories that work on a that are responsible for software working on the hardware, and very soon I still want to believe that we can do it in a week, next Thursday. I understand it is very hard, and if nothing is possible, we'll postpone, but it is very undesirable because we need a month for projects. So where are we now with this? So we are done with first. Now we completely are done with orbitals and charge. The momentum dispersion, we should talk by email to Amir. It's not hard, but the labs go so quickly that time goes by that I just cannot say an extra word. The anions, cations, and excitations, very quick. It will be possible next week, and spin polarized those also easy. The easy but time demanding part is this thermal heating and movies, and UV visible spectra that Stephen volunteered to present has been started yesterday on the lab, and I will continue a little bit more skills about UV spectra today in the class, because we are very far in material, in academic material, but we are behind in the labs. And also the UV visible spectra were a part of the homework, so it will be unfair for me to ask you to do something that hasn't been yet presented. So for in academic sense, I'm pushing the brake on the lecture 22 and waiting until we get more lab materials to get to the presentations of practical skills. So for the homework, right now I want to believe that everyone is able to plot HOMO and LUMO orbitals for any model, right? It is what we considered in the lab today. So I need to tweak the in-car, run VASP once again, and then transfer part charge files from the cluster to the local computer, and then plot them with the VMD software. So this question number 3 seems possible. What we didn't cover is the oscillator strengths and absorption spectrum. So in some sense, at the last 10-20 minutes of the lab, we did cover the oscillator strengths, and I will go over it once again. We didn't show how to convert oscillator strengths in the file OS strengths into absorption spectrum. And I think this is the key skill which we all need for success in the course. So I suggest that we discuss this subject right today in class, as a top priority. If there will be time, I will keep providing academic abstract material after that. But this oscillator strength is a priority. A little of a reminder, because we started to approach this background for oscillator strengths in a previous lecture. So we are considering of system going from ground determinant to excited determinant, for ground state to excited state. Excited state corresponds to promotion of electron from orbital I to orbital J, and matrix element of this transition is a product of initial and final orbital with coordinate operator in between. The Fermi golden rule prompts that if you take this vector of oscillator strength square and multiply it by some constants, then it will be intensity of probability of the transition. And we need this data. We need the energy of initial state, energy of the final state, and probability of this transition to compose the equation for absorption spectra. So the spectra that we will cover in the next minutes will look like x-axis will be transition energy and y-axis will be peaks corresponding to pairs of orbitals. Okay, so the goal of next 15 minutes is to show how to convert the data that we all generated as the last step of the lab, the last 20 minutes of the lab, into equations that are shown here. So there will, not equations, the figures. You do see two panels, but they present the same information. So in panel A, we do have transition energy as the like delta change in energy on the x-axis. On the panel B, we have a wavelength, which is delta energy divided by constant, which some of us may remember opposite. It's a constant 1242 divided by delta E. So you see that they are inversely proportional. So in 15 minutes I will return to the same figure and speak more about it. So I am not going to repeat the things that we did in the lab. I'm continuing from where we did stop. So after performing certain manipulations, we all have got the file that is named os_strengths. And the structure of this file looks approximately the same. So first two columns are initial and final orbital. So each line in this file, in this table, corresponds to a pair of orbitals. The third column corresponds to the value of oscillator strength for given pair of orbitals I and J. First column I, second J. The fourth column will be energy difference between I and J. The fifth column is occupation of orbital I, we can call it, let's say, P, probability that population of at orbital I, and here's population at orbital J. So right now we do see that both these orbitals are occupied. The code does compute oscillator strengths for them, but they are not very much important. We are going to remove this line very soon. The last three lines are x, y, and z projections of the transition dipole moment. So dx, dy, dz. So if you take these three numbers, square of each of these three numbers, add together and multiply by constant, we will get the probability of transition oscillator strength. Now let me focus your attention onto the columns 5 and 6. If we scan through all possible pairs of orbitals, you can see that there are situations when both of them have 2 electrons. There are situations when both of them have 0 electrons. For example, it is if both of them are above LUMO. And there are very healthy situations when first orbital, initial orbital, is occupied and it has 2 electrons, and second electron, target orbital, is unoccupied. So we need only such data. We need transitions from occupied to unoccupied, because what happens if our system is in a ground state and it obtains a quantum of energy that can promote electron from occupied to unoccupied. So the next couple of lines, and we will repeat it on the lab on coming Wednesday very quickly along these lines. So we are parsing such lines that contain 2 space 0, and then we will call it new oscillator strengths. So what I'm suggesting by this operation, that I'm putting a little star nearby, we are removing transitions from occupied to occupied and from unoccupied to unoccupied. So we keep only relevant transitions from occupied to unoccupied. So as soon as this operation is done, we need to convert set of this data, and the example that I'm showing, there are only 3 lines, but in fact this file is number of records in this file is number of orbitals squared. So if your model has 20 orbitals, then this file will be approximately 400 transitions. So it is, if your system has 1000 orbitals, it will be 1,000,000 transitions. And as soon as this file is ready, we need to measure how big is this file. So WC means word count. So in the specific case that I'm presenting here, upon parsing only transitions from occupied to unoccupied, we have 28 lines, 28 records. Then the next command, you can just copy paste it, but the meaning of this command is that we are going to change we are going to focus on the codes that were compiled with free GNU compiler, if you're curious. And then we are going to run a code which is very similar to our procedure, how we converted the file states into the file density of states, DOS. So we need to convert discrete set of data into continuous distribution. Why? Because if there are more than 10 data points, human eye is not the best way to analyze data. And since all this data are quite regular, it makes sense to convert them into continuous distribution on one hand. On another hand, the continuous distribution that we are going to produce will be exactly the linear absorption UV visible spectrum that is possible to measure on experiment. I do not see among today's attendees Salim, but he should be mostly happy about it because his primary research duties are to measure absorption spectra. So before we use codes to convert discrete states into continuous DOS, now we are converting discrete oscillator strengths into continuous spectrum. So in a similar fashion as it was when we created density of states, the code is going to ask some silly questions. So the question number 1, it wants us to type how many transitions, how many lines are in the oscillator strengths. We are answering, okay, 28. Second question, it asks in which range we want to explore spectrum. So infrared is from a very small number to like 1 eV. Visible is from 1.7 to 3, and from 3 to 20 electron volts is UV. Practically reasonable range is from 1 electron volt to 4 electron volt. The next question is set up a width of each line. So in the same way as it was in the density of states, we do have the transitions at certain values of energy, and their height corresponds to oscillator strengths. But we do want to assign a continuous width to each peak. Why? Because there are several, well, first it will look more beautiful. Second, there are natural reasons for energy of each transition being not fixed. So one of the reasons is thermal broadening. If we launch molecular dynamics, if we let each ion to move, then transition energies will oscillate in time, and in average it will be a little bit to the left, a little bit to the right. So we can set up a width parameter that gives this thermal broadening. Another mechanism is inhomogeneous, when we want to describe an ensemble of many systems. So this parameter can be selected by some small fraction of electron volt. Then next question is, what is the number of HOMO for the system that you are considering? So for our model of titanium 2, oxygen 4, periodic nanowire, the number of highest occupied molecular orbital is 16. You already remembered. So after that, the script is reading the oscillator strength file and generates the file named spectra. If you do hate GNU plot, you can download the spectrum file and plot it with Excel or Origin. It will include the data for spectrum figure like this. Just in case, if someone is interested, the columns in this file will be wavelengths of transition, energy of transition, intensity at given energy, and the rest is not needed. So next part is completely practical thing. It does belong to the lab, but since our lectures are ahead of the schedule and labs are behind, I apologize for showing practical non-academic skills in the lecture. So as soon as we have the file spectrum, we need to plot it. So we are performing plotting with very ancient code GNU plot, and we are using a very brief script. You are very welcome to look inside. It will be about 5 lines, and it is very similar to the script for plotting density of states. So we are typing GNU plot space path and this GNU pro underscore SPE, and then we can do the same for SP underscore NM. This procedure will, these two procedures will generate the files SPE.ps, which is an ancient format for graphical information. And in the next line, we are converting the PostScript into PDF. As soon as these two files are completed, we are done with the spectrum. Before we are looking on them, we are transferring these PDF files to the photon cluster, and then from the photon cluster, we can transfer it to the local computer. So here are the two files. I'm done with boring part. Now it will be more fun part. Other questions on this boring part? Okay, I do not see any questions. Going to the fun part. So this slide is worth of speaking about it for a substantial amount of time. The lower panel contains the file SPE.pdf. The upper part of the slide contains the file post strength. In order to analyze this data in a more reasonable way, I am looking on transitions with lowest energy first. So for this purpose, I sort minus column number 4. It will slightly rearrange. So after this rearrangement, the transition from HOMO, which is 16, to the LUMO, which is 17, floats to the top of the displayed table. One of the questions for the homework was to find oscillator strengths for the HOMO-LUMO transition of the given model. So this yellow highlighted thing, point 17, is value of oscillator strength for HOMO to LUMO transition. So if you have, if you do previous steps for the models that you are focusing on, then this number is what needs to be reported. Now, what is the correlation between this table and the image that we show on the bottom? So line number 4 is transition energy. It shows here the value 1.7. So 1.7 is about here. The width that we have assigned is here. The height of this peak is determined by this yellow number. So if calculations are performed correctly, then which I doubt, it could be this transition energy is a little too low for this material. It should be a little higher, but right now we are considering practical aspects. So if calculations are computed correctly, then such spectrum would mean that the model is going to absorb light, which will be like on the border between the red and infrared, at the transition energy of 1.7 electron volt. This transition corresponds to electron moving from occupied orbital 16 that we were plotting during the class. So it is on oxygens with blue to the orbital number 17, which is localized on titanium, and it is shown here in red. So due to photoexcitation, due to light quantum, h nu equals 1.7 electron volts, the electron from orbital 16 is jumping to orbital number 17. And if one performs this on experiment, if one runs UV spectrophotometer, one would get this spectrum. Please ask questions if any. Okay, if no questions, I'm going to the next slide. So the next peak corresponds to next line in the table. So next transition is at 2.3 electron volts, and it is about 5 times more intense, 0.78. So this peak is higher. If you go to the next transition is at 2.6, and the intensity of this transition is lower. So the peak is lower in intensity. One more comment. So it is the slide we started from. Dependence on transition energy and on the wavelengths. So since wavelength is a constant, 1242 divided by delta E, since nanometers, it is inverse to the energy, the peaks in the spectrum are arranged in the opposite direction. They go to the smaller values from larger value of wavelengths to small values of wavelengths. In the spectra which depend on transition energy, we are going from small to the large energy. But the peak, let's call it maybe peak number 1, or we can call it just HOMO transition the peak number 1 in the dependence on energy corresponds to peak number 1 in the dependence on wavelengths. Peak number 2 in the dependence of energy corresponds to peak number 2 in the dependence of wavelength. So another language that spectroscopists are used, they are calling transitions with lower value of energy and bigger value of the wavelengths. They are calling red transitions, and it doesn't mean that it is literally red part of the spectrum. They to the more red part of the spectrum, and with the bigger transitions, they are called blue part of the spectrum. So if we screen the rainbow color wheel, like red, orange, blue, it will go from smaller to larger energies. And if you go in wavelengths, it will go from bigger to smaller values. Any questions to this part? Okay. We are done with the practical skills, and please consider to use them towards the homework. Feel free to stop me and ask questions now or by emails. And what I'm going to present next is, I wouldn't say it is not needed, but it is of smaller practical importance compared to what we considered right now. So this absorption spectra are truly important part of the course, and they will be part of the projects. The subject that I'm going to show right now is also needed, but only to those who is planning to describe magnetic materials, radicals, systems with transition metals. So last time we went over simplest possible functional local density approximation, and the goal of the academic part is to come to this equation into the red box. In order to speak about this equation, we need as a minimum to get definition of all symbols there. So LDA stands for local density approximation. LSDA stands for local spin density approximation. We already get an idea what is rho, what is integration over R, and we need to define what is Cx coefficient, and especially what is this Greek letter that a lot of people get confused how to pronounce it, including me. I think we can pronounce it as psi. In Greek language, it is the letter that is used in the name Alex, like X, K, S together. So if by the end of today's meeting, or maybe if we need to postpone by the end of sometimes on the Tuesday meeting, we get all components sufficient to describe what is this psi and where this equation comes from, we should be able to describe magnetic materials with density functional theory. So magnetic materials have unpaired spins. And this is about where we stopped last time. So the two components in the wave function of the same spatial orbital for a spin up, plus 1/2, -1/2, or alpha and beta, need a set of operators like S plus and minus to flip the spin, and by linear combinations of these plus and minus spin operators, one can get magnetic projections, Sx, Sy, and Sz. If we do have wave function with alpha and beta projections, we can convert wave function, or better, instead of wave function, is better to say orbital. We can convert orbital into probability distribution, or in this theory, it's better to say into density. So if we multiply this little vector with alpha and beta component as a row by column, we get a summation of density corresponding to alpha projection and density corresponding to beta projection. This little box does correspond to the exercise that we did yesterday in the lab. There were questions about VMD, plotting of the orbitals, and there was a question of volumetric data. It was asking to use up plus down, and then there were more options. So what we were plotting in our last lab was that corresponds to this alpha plus beta. So even if our system would have spin, if we add together contributions to the density from alpha and beta spin, we get total density, alpha plus beta, up plus down. If we perform, instead of row by column, if we do column by row, then product of the vector in itself gives a matrix 2 by 2, and the components of this matrix are alpha alpha, beta beta, and cross components alpha beta and beta alpha. So it is where we ended last time. So the following thing could be of interest to Steven, if he is on connection. Yes, I see Steven is on connection. So it is how to find the energy of interaction between our system, which may have spin, and magnetic field. So it is a scalar product of magnetic field times vector of a spin, which consists of 3 projections, with minus sign and Bohr magneton. Why this discussion is coming to our focus? This is not empty curiosity for the curiosity. It is an important step which is needed for most of the approximations that most of the practical computations of magnetic materials. Here we are considering general situation when projection of magnetic moment created by spin can be oriented anywhere in the space. But in 99.99% of the practical calculations, one is making an approximation that magnetic moments and spins can be oriented only along z axis. This is a substantial shortening of the natural phenomena, but it is most typical way to arrange practical computations. So in case we take as an approximation that we permit the magnetization and the spin to be aligned only parallel to the z-axis, then the energy of interacting between spin and magnetic field will be B sub z projection of magnetic field times z projection of S sub z projection of a spin minus and multiplied by -2 Bohr magneton constant. How one can express this energy out of wave function or out of density? Right now, I'm going to give something boring, abstract, and academic. I invite everyone to lean back and relax, and I will give a note when there will be something really important to focus on. Okay, I'm continuing. We are looking onto the energy of interaction between spin and magnetic field. Why do we need it? Because if we want to assess magnetic properties of material, the energy of interaction is one of the observables. How can we express this energy of interaction between magnetic field and spin in terms of orbitals, or better, in terms of densities? There are several ways to find expectation values in general. So most typical for continuous wave function, you take bra and cat, wave function with star, operator, wave function, and integrate. If wave function is represented as the continuous vector, two components, we do row, column, and matrix of operator in between. So if we do know orbital these components, then we do need to know matrix elements of the operators that we are looking at, and then we just compose this row by matrix by column. The same operation can be performed in the language of density matrix. This is most boring, most academic, and most out of our focus thing. So if one knows the density matrix, which is stuff that we already introduced in our specific case, like rho alpha alpha, rho alpha beta, rho beta alpha, rho beta beta, and if you do have the matrix of operator, we need to multiply these two matrices and take trace, which is a sum of diagonal elements. And if we perform this operation, the result will be the same as if we would do more standard ways. So while preparing this lecture in the past years, I did this little exercise. So our operator, magnetic field along z-axis is a constant. The operator is z projection of spin, which is 1/2 on the first place minus 1/2 on the last place, and zeros on the off diagonal. So it is a first matrix. Second matrix are this 4 density matrix elements corresponding to a spin. And if I perform this multiplication of row by column, I parse only row alpha alpha and row beta beta. The alpha beta and beta alpha cross terms disappear because of the specific of this SZ operator. And if I find an expectation value of SZ value, then it comes as a subtraction of density of spin up and density of spin down. It is very important that cross terms obtained by product of alpha times beta and beta times alpha are not needed if we are looking on Z projection of spin, are not needed if we are looking onto the interaction of magnetic field along Z with our system. So through this derivation, we can prove that we do not need to be too general. For this specific question, we can get rid of the spin components in X and Y directions. We really, for energy of interaction between spin and magnetic field, we need only components of density alpha alpha and beta beta, which are probabilities that system has that in given orbital spin has alpha spin minus probabilities that it has beta spin. For example, if we have a doublet with spin plus 1/2, then this rho alpha alpha will be 1, rho beta beta will be 0. And then this energy of interaction with magnetic field will be substantial. Please tell into your microphones if this makes sense. I have a little fear to get too quick or get logical disconnection from the audience. Yang Chao?
Yes.
Do these things make sense?
Yeah.
Okay, good. Raju? Do you have any questions, or you need time to develop them? Okay, Raju is thinking. Rebecca?
Yeah, it makes sense.
Okay, good. Thank you. Thank you. Amir?
Yeah, it's okay.
Okay, thank you. I'm very happy by your support, because I started developing fear that I'm going too far. Zhaofan?
Yeah, I think it makes sense, but I cannot fully understand.
Okay. On the next lab, I plan that we will do practical computations related to the things, and maybe it will get us more confidence. Steven?
I think I'm with Zhaofan. It makes sense, but I'm not sure I entirely get it.
Okay. Thank you for the support. So, before we were speaking only about the one orbital and alpha and beta projection. Next Wednesday, I will try my best. I will do my best so that we do spin-enabled computation with VASP, and it will be to some sense similar to what we did spin-enabled computations in Gaussian. There will be two sets of orbitals. One for orbitals for spin alpha, another set of orbitals for spin beta. Right? And the main feature that if the model is open shell, if the spins are not compensated, then the orbitals may look different, like for orbital 1 alpha and orbital 1 beta can be different, and so forth. And another thing, that the highest index of highest occupied orbital for alpha and beta could be different. Like if you have more alpha, more spin up electrons, more spin up orbitals, occupied orbitals, then spin down electrons, then these two, the HOMO alpha and HOMO beta, will be two independent numbers, and they will be not equal to each other. Okay. Then one may compose a density out of all spin alpha orbitals on one hand. On another hand, one can compose a density out of all spin beta orbitals. And we do it in the same way as we did before. So absolute value square as function of r of each orbital, and then adding together all occupied orbitals for spin alpha, and the same procedure for spin beta. So if we do this densities for spin alpha and density for spin beta, they will be used as independent parameters, as independent arguments for the functional. So the total energy of the magnetic system will depend not on the overall charge density, but on the density of electrons with spin alpha and density of electrons with spin beta. And this is highlighted in this equation at the bottom. So there is not much information, but if you think that our heads are getting overwhelmed with new information, we can make a stop at some point. Okay. So what if we take density of all electrons with spin alpha, all electrons with spin beta, and integrate over space? I know that I'm asking a silly question because answer is here. If we see from the previous slide, integration over orbital absolute value square gives 1 if the orbital is occupied. If you have n sub alpha occupied orbitals with spin alpha, we'll get from this term, we'll get n sub alpha. If you have so many occupied orbitals with spin beta, we get n sub beta. By adding together these two things, it will be total number of electrons. If we practice a minus sign in this expression, we will get a subtraction of electrons with spin alpha and electrons, number of electrons with spin alpha and number of electrons with spin beta. In case this number equals 0, it means all spins are compensated and system is in a singlet state. I believe that the next table is what we did on the last lab on the Gaussian about 3-4 weeks ago. So if we subtract number of electrons alpha and number of electrons beta, it will be like delta n, difference between alpha and beta. If we accept that a spin has a value of 1/2, then we take this delta n and divide by 2. It will be length, total spin in the system. Not projection, but total spin, absolute value of a spin. We do not care where it is oriented. So if delta n is 0, then spin is 0. If delta n is 1, spin is 1/2. If delta n is 2, spin is 1. If delta n is 3, spin is 3/2. Okay? Now, there is a concept of spin multiplicity. So how many individual states can be are allowed to exist with a given spin. And this simple equation of multiplicity is 2s plus 1. So if all spins are compensated, if it is a singlet, 2 times 0 plus 1 will be only one state. There is no ambiguity. If there is one unpaired spin, it can be oriented up and down. So multiplicity is 2. If the total spin is two unpaired electrons. Total spin is 1, and by laws of quantum mechanics, it can have 3 projections: all up, all down, or triplet state when they are symmetrically compensated. So 3 states. 2s plus 1 equals 3. And then for 3 unpaired spins, there are 4 states. And depending on this multiplicity, one can call them singlet, doublet, triplet, quadruplet. So we are approaching to the chance of describing spin and multiplicity in VASP software. In Gaussian software, we use just one number for charge and one number for multiplicity. Like most typical was 0, 1 for neutral, singlet. In VASP, there will be different keywords for spin and multiplicity, and I don't want to keep long intrigue. Let me just write down these keywords here, and I will check if everyone will be happy to make a break here so that we do not overwhelm our memories. So for charge,
excuse me, after 12, I'm busy with another course. May I leave?
Yes, it is what I'm suggesting.
Okay, thank you. I will watch the course tutorial later.
Yes.
Thank you. Have a good.
Yeah, you do. So for the charge, the VASP keyword is number of electrons. If one wants to do open shell, one needs to type I spin. It's same like iPhone. I spin equals 2, because there will be 2 components. And if one wants to select this difference of spin up and spin down, one needs to write n up, down, and up, down, and then write the number which from this table. If you still need a singlet, write 0. If you need doublet, write 1. If you need triplet, type 2. Okay, let's move it into here. Yes, I suggest that we are announcing stop at this point, and everyone, thank you for your dedication to the course. Everyone is welcome to disconnect and depart. I will stay connected just in case if there are some questions.
Thank you.
Thank you, Rebecca.
Thank you.
Thank you.
Thank you, Professor.
Thank you. My pleasure. Okay, I do not see questions. I'm going off the record. Mason, many thanks for the support.